Welcome back to Chapter 0. This time we're going to be looking at Section 6, which is the last section in Chapter 0. And this section is on trigonometric functions. So we're going to see radians and trig functions and all sorts of great stuff in a relatively short amount of time. It won't be anywhere near as depth as pre-calculus because we don't use quite as much and you already know this stuff. So first we're looking at our learning targets. You can convert between radians and degrees and solve trigonometric equations graphically. So solving an equation graphically is just graphing it and seeing where the intersection is. It doesn't matter what kind of equation, that's the same. Determine whether functions are even or odd and explain graph symmetry. We've seen that too, just not with trig. Answer questions involving arc length. Find trigonometric values of angles using given conditions. And graph trigonometric functions. So, the first thing we're doing is looking at radians, and converting between degrees and radians is a simple ratio. We know that in a full circle, there are 360 degrees and 2 pi radii. It's a ratio. You make it degree over radian. You know one of the either the degree or the radian, you plug it in, and you can cross multiply and get your answer. Generally speaking, we reduce that 360 over 2 pi to be 180 over pi equals degrees over radians. And again, it's the same thing. You just plug it in. Generally speaking, with our radian measure, we keep the pi, but not always. So if it says something like 2 radians, then it's 2 radians. 1 radian for estimation purposes is about 60 degrees, by the way. So we have arc length. The arc length. So the arc length is a circumference. The circumference is 2 pi times the radius. Well, that's all the way around. We might not want all the way around. So maybe we only want part of an angle. Well, what's beautiful is in radians, an arc length is just the radius times the angle. So if we have a radius of 5 and the angle is 2 pi over 3, I guess let's say the radius is 5 meters, it should have units, angle is 2 pi over 3, the arc length will be, you just multiply those. 5 times 2 pi is 10 pi over 3 meters. That's a time when you probably want to multiply out the pi, because if you're finding the arc length, it's usually a distance that is going to be needed a little bit more than that. And then we have our trig ratios. Now it could be in a triangle, right triangle, we have our opposite, our hypotenuse, our adjacent, and our hypotenuse. Or we have a circle. And it goes out. We have the x value, the y value, and the radius. We're going to look at more of the circle one this time, but notice it's the same thing. So, trig ratios, we have 6 of them. Sine of theta, and theta would be the angle in there, the center angle, is going to be, it's opposite over hypotenuse, it's y over r. Cosine of the angle is x over r. Tangent of the angle is y over x. So in a unit circle where the radius is 1, the sine is the y value, the cosine is the x value. Regardless of the radius, the tangent is actually the slope of the radius. It's the rise over run of the radius. Our other 3 are the inverses. So we had sine, we also have cosecant of theta. It's just going to be r over y. Cosine gives us a secant of theta. It's r over x. And tangent, it's going to be a cotangent of theta, which is x over y. And so those are just the reciprocals of the three trig values, the three trig ratios. We have graphs of them. So the graphs of these we've seen before. Sine and cosine have this sinusoidal graph. That's what that wave is called. It's a sinusoidal graph. We have transformations that we can do with that. The transformations are identical to transformations that we would do on anything else. The tangent and cotangent graphs, these two look kind of like cubics, but they're asymptotic. All the rest of them have asymptotes. So the tangent and cotangents are the ones that go up or come down. The secant, cosecant, and secant graphs are, if we take the inverses of sine, when I'm graphing these, I would first graph the sine, because the sine is going to hit 0 at the asymptotes, and then it actually goes up and hits those. So I would graph the sine. The sine's easier to graph. Then you put the asymptotes where there's zeros, and then you make the u's. Same thing with the cosine and the, well, that was the cosine. It's cosine was here and sine was here. I wasn't looking, I always just assumed sine then cosine. So the secant, you draw the cosine and it matches. Same thing with the sine, you just put the zeros. And then there, and then I would draw the u ones from there. But generally speaking, you're not going to be drawing these. Like these ones, you're going to graph them, but you need to know the shape because graphing calculators don't do asymptotes particularly well. All of these graphs have what's called the periodicity. It's the period. And the period is how long it takes to repeat one full cycle. So to get from the maximum to the maximum. For all of these, it's 2 pi, as we can see down below there. The tangent and cotangent, it's actually pi. So it actually repeats twice in the 2 pi range. So the period is just this distance. It's a distance to get from the middle all the way to the top, down to the bottom, back to the middle, or it could be from the bottom to the bottom. That distance is the same, but that's one full cycle. When we do a horizontal stretch, it will stretch that period. When we do a vertical stretch, it stretches the height, which is called the amplitude. The amplitude is that height from the center up to the top, or it's half of the distance from the lowest point to the tallest point. But those are all transformation things. We've seen transformations a ton. These transformations work exactly the same. Except a horizontal translation is called a phase shift, if you remember that. Then we also have inverse trig functions. So the inverse is what we looked at with inverses in the last topic. The symbol is that -1 exponent, and it switches the x and the y's. Graphically, what an inverse does is it reflects it over the line y equals x. We'll see the graphs here in just a second. We actually have to limit them, otherwise they're not functions, and we like to deal with functions. So we limit them to be functions. That's why the domains are limited, whereas the other ones, they weren't. So we have our 6 inverse trig functions, the various domains, the ranges. We don't use these anywhere near as much as we use the normal trig functions. So these are here. You can look at them. There's nothing particularly exciting. And then we have graphs of the inverse trig functions. Notice the inverse cosine, like the cosine, it keeps going in that wave pattern. Well, we've restricted it to make it a function. Otherwise, it would keep going up this way and back down this way forever, but we don't want it to do that. And so that's why the domain and range are restricted. And the same for all the rest of them. So that is the inverse trig. Again, you can look at this. This just came straight from your book as well. You can look at it in your book. But those are the graphs of the inverse trig. We don't use those anywhere near as much as we use the regular ones, as I said. But today you're going to be looking at using that arc length formula, doing some conversions between degrees and radians, graphing some of the trig functions or matching graphs, depending, and just kind of getting a little overview of trig. In calculus, we're going to see it. Like trig questions will just pop up from time to time, just all over the place. It's not like a big trig section or anything. So it's important to have a good feel for these graphs and functions. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.